Hello everybody, this time I will solve this problem. What is this problem? It is about finding the maximum axial stress, say maximum axial. So what is the maximum axial stress and maximum shear stress for this beam? What this beam is, it has a uniformly varying load, a concentrated load, and the section of this beam is this. Hopefully you understood what the beam is. Again to remind you, this is a simply supported beam with two loads, and this is the section. We need to find the maximum axial stress, maximum shear stress. Okay, let us start. Before starting, let me tell you what is our objective. Our objective is to find the maximum axial stress. What is maximum axial stress? Summation of bending stress and normal stress, and then maximum shear stress. Okay, so yes, before starting, let us see if this is our section. We know that for this section, our neutral axis is somewhere here, neutral axis, and if I draw the maximum shear stress, it is roughly this. So that is the maximum shear stress diagram, roughly, yes. And then what is the maximum? And maximum bending stress diagram is roughly this. This part is sigma MC over I, sigma MC over I. Now C1, C2. Here to here is C2, here is C1. So that is the schematic of shear stress diagram, schematic of bending stress diagram, and for normal stress diagram, it is typical homogeneous. Sigma is N by A. So what is our objective? Our objective is to find this maximum shear stress. Then the summation of either this value and this value, it is bending stress, normal stress, summation is axial stress. Then we will find this value and this value and compare this set and this set, whichever is greater. That is called, so this is axial and this is shear stress. So we will find that. Okay, before finding something to tell you how to find this. So this one to find is gamma is PQ over IT. B is maximum shear stress, I is moment of inertia, T is thickness here at this point, that means here, and Q is EY bar, that means area below this area, and then centroid of this area is called QQ. Okay, so long story short, we need to find our Vmax, we need to find our moment of inertia. Okay, we will find it. For this, what do we need? We need maximum moment of inertia. And C1, and then C2. Now C1, C2, there is no universal name. We can call this C1 and this C2. No matter. As long as you understand that if I use C2 means this distance, I will get this stress. So we need to find maximum shear force, maximum moment, and maximum normal force, moment of inertia. So let us find those first, then we will come back here. So to draw the normal force, shear force, bending moment diagram, we have to determine the reaction curve. Say this is By, this is AY. So if we take summation of moment at A is 0, say clockwise, moment positive, my first force is triangular, 10 kg/feet, it is working in 9 feet. So this is my force, this is my lever arm, I can add my lever arm somewhere. So 10 kg/feet in 9 feet. And it is working 3 feet here, 6 feet there. Because for triangle we know that center is at 2/3 and 1/3. Okay, so 6 feet here, clockwise, positive. Next force is 40 sine 30, and distance is 9 plus 15, and then my next force is By, and that is 21 feet. Okay, can you see? Let me check. Yes, so hopefully you understand what I do here. I took moment here. My first force is this force acting at 6 feet. The next force is this force, this component, 40 sine 30. Distance is 9 plus 5 plus 6, 15. Now why I did not take this component? Because this component is going through this point. So 40 cosine 30 has no value. Then By counterclockwise minus. After solving, how much is my force? I already solved it here. After solving, I got 27.1. 27.1 kilo. And then if I apply summation of Fy is 0, say upward is positive, and Ay I assume upward minus downward is 10, Q/P 90, then minus 40 sine 30 plus By is 0. By I already know it, and after solving I got Ay is 37.9. 37.9. Okay, I got By, I got Ay. Then I need to find my Ax. Say my Ax is here. How to find Ax? Summation of Fx is 0. Then Ax positive, this way is positive. That side I am assuming positive. Ax this way minus 40 cosine 30 is 0. Then I got my Ax how much? 34.64. 64. So I got my support reactions. Here two unknown, why? It is a pin support. Here one unknown, why? It is a roller support. So I got my Ax. Now my Ax is going this way. My Ay is upward. By is also upward. Now you should be careful in determining the support reaction, as if it is wrong, everything else will be wrong. So make sure it is correct. Check it, double, triple, whatever time you have. So we got my support reactions. Now we will draw the shear force diagram, bending moment diagram, axial force diagram. Why? The reason is we have to find the maximum bending stress, maximum shear stress, maximum normal stress. That depends on maximum moment, maximum shear, maximum axial force. But I do not know where is my maximum axial force. If I knew by magic or whatever that my maximum moment is here, then I can cut here and find the maximum moment. But I do not. This is why I need to draw the diagram. Okay, start drawing diagram. 34.64. I will write down here. So this is 34.64. This value is 37.9, and this value is 27.1. Okay, now I will draw the diagram. So first I will draw X saying feet. My axial force diagram. What is my axial force diagram here? I have force here this way. So that is compressive. And my force here, there is no other axial force here. After that I have axial force here. So that means this is applying force this way and that is applying force this way. So this portion is under compression and the value is, so this portion is under compression and the value is 34.64 kilo. So this is a negative value. So only this portion is under compression, there is no axial force here. Okay, then we will draw shear force diagram. Again, how to draw shear force diagram? Find your reaction, follow the rules. What is first? What is my first force? 37.9. It is up, so I will go up. 37.9. I am drawing a shear force diagram in KIP. Shear force diagram. This is my X feet. So my first force is 37 positive, so I went up. Force is up, I went up. Then this is telling me go down, go down. How is the uniformly varying, not linearly. At the beginning, very small load, after sometimes huge load. So I will go slowly here, okay, slowly here, and then suddenly. Now after coming here, when I come here, we do not know. So let us calculate that. I have 37.9. I will go down how much? Whole load. Half 10 feet times 9 feet. How much? 37.9 minus 45. That means how much? I already calculated to save some time. It is minus 7.1. So I am doing minus 7.1. That means after coming here, I will do minus 7.1, which is here. So minus 7.1. Say here. So I'll come very slowly. I will go down very slowly here, then suddenly here. I got minus 7.1. Okay. There is a point where shear force is 0. We know that whenever there is a shear force 0, at that point my moment is maximum or minimum. So this point is very important. We should know this distance. Okay, we will find it. So this distance, we will find it. And now let us finish it. Then what I will do? After that, I have no load here. No load here. So what I will do? I will continue the same. There is no load here. That means nothing to do. Keep the same. After coming here, what is happening? It is telling me, this component is telling me go down. How much is that? 40 sine 30. So I will go down by how much? 40 sine 30. So I have minus 7.1 and I will go down by 40 sine 30. How much? And we calculated 27.1. So 27.1. Why? 40 sine 30 is 20. So we got 21.7. And we going down. After that, no load here, so nothing here. Keep the same. After coming here, this one told me go up 27.1. So up 27.1, we came to 0. So our diagram is a closed loop. So whatever we did is right. So that is the way to draw shear force diagram. Then we will draw bending moment diagram. Oh, before that, this point is very important. How to find it? The way I find it is, I had a value of 37.9. After going some distance, my value is 0. How to find it? That means, say, my value was 37.9. After going some distance, say this distance, say this is my x. Say this is my x. So after going x distance, my value becomes 0. That means this area of the load is actually this. What is the area of the load? If this is x, what is the height? You have to find this value. If I go 9, I am getting 10. That means, okay, write it down. I am getting 10 if my distance is 9. So if my distance is, what is the y value? X. So this is y and this is x. So from similar angle triangle, Similar angle triangle, that means if whole is 9, I am rising 10. If this portion is x, what is my rise? Y. So y by x equal 10 by 9. So y by x 10 by 9. So my y become 10 by 9x. So 10 by 9x. This value is 10 by 9x. So my load is x 10 by 9 and then x equals 0. If I solve it, what I will get? I will get 8.26. 8.26 feet. So this value is 8.26 feet. Now this point is important because my moment is maximum or minimum here. Okay, hopefully you understood what I did. I had a value of 39.7, it is going down. So after this load, my value becomes 0. So we have to calculate the area of this load. I assumed x, found my y, then the area of this half base height. Okay, 8.26 down. I do not need any more this one. Now we have to draw our moment diagram. And we found what is our maximum moment? 37, 21. So this is our maximum moment, Vmax. For moment, positive, negative doesn't matter. We should consider the maximum one. Now, why positive, negative doesn't matter? Positive moment means this portion will go down. That is positive. Negative, sorry, not moment, shear force. Positive shear force means this portion will go down. Negative shear force means this portion will go up. So up down doesn't matter. The stress is the concern. So we should be concerned about maximum shear force. Once this is done, then we will draw moment diagram. What is my moment diagram? So this is again say distance. Moment diagram is summation of area of shear force diagram. So at the beginning my moment is 0 because that is a fin support. Fin support cannot take any moment. So moment is 0. Or what is the area of our shear force diagram at the beginning? Nothing. If x is 0, no area. 0. Then I will come here somewhere. What is my area? Now this is a oval shape. We can calculate exactly, or we can consider the approximate area. So approximate area, we know that if it is linear, the area is RPH. If it is this shape, area is 2/3 PH. If it is this shape, area is 1/3 PH. Now this is approximation. We can use it for our case, but if we want to be precise, we should cut here, draw the find the internal maximum moment. We can do that also. So let us see what is my maximum moment here. So that portion is, so we will use this rule, 2/3 PH. That means 2/3 P means 8.26, and then height is 37.9. How much I calculated previously? It's roughly 209. Roughly 209. Keep it. We do not need to be so precise here because we have so much safety when we design beam, and this approximation will give you very close answer. Now, if you do not believe it, no problem. Cut here and find the maximum moment. How? This value is 37.9, and we are once cutting here 8.26, and then Then what is this value? This value was 9 by x times 8.26. How? Can you remember when we found the y value? 10 by 9 times 6. Then we can find the moment here. So if I do the exact calculation by 9 times 8.26, it is 9.18. 9.18. So what is the moment here? My moment here will be, say, summation of moment at here. At here is 0. Say clockwise positive. Clockwise positive. This moment is counterclockwise negative. 37.9 will give me clockwise moment positive. This node will give me counterclockwise, so negative 8.26. Then what is my load? And then 1/3. So 8.26 divided by 3 equals 0. If I solve it, 37.9 times 8.26. I got my moment is 208.67. So initially we got how much here? I forgot 209 most probably. Now we got 208.67. So it's good, yes. Now here my moment is say 2.9 because 208 is very close to 209. We can round up. Now how will I go there? First of all, when we are concerned about maximum moment only, we are not concerned about shape. But still though, if you want to know, most of my value here, less value here. So go first here. Is not a good shape. This is a good shape. At least not lead here. Most of my node here, less here. Jump first, then approaches slowly. Or here my value is positive, decreasing. So here my slope is positive but decreasing. Whatever the value here, that is the slope here. So value here positive but decreasing, slope here positive but decreasing. Okay, then this area that is negative, and that will keep. We have to find the area of this. How much? So that is 1/3 B is. B means this length. How much is this length? Point very small. 0.74. What is my A? 7.1. We have to deduct this small area, and that after deducting we found up to 2, very small, up to 2. So we'll come here 207. Then we'll deduct this area, this triangular area. After deducting, we got here 166. 166. Now this is a straight line. Why? This value is negative, constant. Slope here negative, constant. Then this one will bring me here. Now we are not concerned about the whole diagram, just the maximum moment. But still I finished it. So maximum moment here is this. Maximum moment. This is the moment diagram in terms of cubic feet. So maximum moment is 209. Okay, now it is our time to find the centroid and moment of inertia, because we found our maximum normal force, maximum shear force, maximum moment. So we have to find the centroid and then moment of inertia to calculate the stresses. Before that, Okay, no. Start how to find centroid of this. Say this portion is 1, this portion is 2. Say this is my reference line. Say y bar is y1, a1, y2, a2 divided by a1 plus a2. What is my y1? Centroid of part 1 from this point. So it is 6, that means up to this is 18. Up to this is 18. So y1 is 9. What is my area 1? 18 times 6. So 18 times 6. Y2 is here from here. That means here is 6 up, 3 is here, 18 is here. So 21 is, my area is 28 times 6. 28 times 6. 8 times 6 plus 28 times 6. And I already calculated it and I found it 16.4. If everything is right, 16.4 is. That means my centroid is roughly here. This value 16.4. So we got our centroid. Now we need to find the moment of inertia. Okay. I do not know whether I made a mistake. Let me check. Should be okay, means. But you can do your own calculation if I make some mistake. But okay. Oh, 16.4. That is my centroid. Now I will find the moment of inertia. How to find it? Moment of inertia of section 1 first, about its own centroid, and then transfer it to the composite centroid. Then, so that is moment of inertia for part 1. How? B is 2 by 12. B is 6, A is 18 divided by 12. That is the moment of inertia of part 1, this portion only, and about its own centroid. I have to transfer it to the composite centroid. How to do it? Area of this, area of, so that is B1 A1 cube by 12, that is area 1. Then how to transfer, what is this distance? In short, we know y bar minus y1. So what is y bar? 16.4 minus y1 was 9. So we can memorize this rule or we can memorize this concept. Whatever way you better understand. Simply B1 is 1 cube by 12 plus A1 y1 minus y1 square. Then similarly for second part. Oh, so what is the second part? Second part will be B2 H2 cube by 12 plus A2 y bar minus y2 square. What is that? So B2 means 28, 28 H2 by 12. What is the area? 28 times 6, then 16.4 minus 21 square. So you can use memorize the rule or you can memorize the concept. First determine the moment of inertia at its own centroid, then transfer it here. Similarly for second one, determine here, transfer it here. And that transfer, small amount is y bar minus y1. For second one, y bar here minus y2. So we will get this distance. Okay, so it is done. After calculation, what is my moment of inertia? I calculated 12,899. 12,899 is to the power 4. Sorry, is to the power 4. 12,899 is to the power 4. So I got my centroid. I got my moment of inertia, maximum moment, maximum shear, maximum normal force. I can find my stresses now. Okay, let me erase it. Keep the value only. Okay, so what is my 1289 is 4. Now, where is my maximum moment? Here, 209. Now, my shear force is not dependent on them. Shear force is separate. Let us find my shear force first. So, in this section, where is the maximum shear force? We know that maximum shear stress. Maximum shear stress is always at the neutral axis. Always at the neutral axis. So, what is, okay, if I draw the diagram again, so this is my section, my neutral axis is here, maximum shear stress will be here, and the approximate shape is, it will go this way, then this, and then come here. So this value, VQ over IT. How to find this value? So simple, and let me write it down here. So VQ over IT. What is my V? Maximum shear force, 37.9 K. What is my I? I is 12,889 inch cube. I. What is my T? This thickness here, how much? It is 6 inch. 6 inch. T done. What is my Q? Area below or above the neutral axis times its own centroid above this axis. So this area is easier rectangle. This is T typical. So this area for okay. Q. What is Q? So Q is, if I write Q A Y bar. What is my area? This portion. What is this portion? 16.4. I'll move it somewhere. It's so congested. Okay, what is this area? 16 times 4. What is the centroid of this area? 16.4 by 2 from the combined centroid. That is my, I made a mistake. My area is 16.4 times 6. I forgot this width. So that is my A, that is my Y, and this is my Q, AY bar. Okay, let us find the AY bar. This portion I did not calculate earlier. Any so 16.4 times 6, that is Q. So right here, Q is 807 inch cube. So this is forces in K, inch cube, inch 4 inch. So my answer will, whatever the answer, it will be K per inch square. How much is that? 37.9807 divided by 1289 divided by 6. I got roughly 0.396 or 395. Okay, if you want to be precise, that's also good. 395. That is my maximum shear force. So one answer is done. One answer is done. What is my maximum shear force? Done. Then we will have to find the maximum axial stress, which is summation of normal and bending stress. Okay. So where is my maximum bending moment? At this point. Here. And at this point I have some normal stress. So I will check. Okay, so this answer is done. I will erase it. So what is my normal stress? Sigma n, n by area. What is my n? My normal force, 38, 4.64, and that is compressive negative. What is my area? Total area of the section. Can you remember? I cannot remember. It was 6. My dimension I can remember here. It was 28. This was 6. Here to here was 18. Then I can calculate my area is 6 times 18 plus 28 times 6, 276. So my area is 276 inches square. This value is in cube. So 34.64 divided by 276. So my normal stress is 0.726 kSI. Now this is not the maximum axial stress. It is just the normal stress, and it is in compression. Now we will find the bending stress. Here it is this. So did I go through the bending stress is linear and 0 at the neutral axis, maximum at the fiber. Okay, better to remove some space here. 0.126. So this value is minus 0.126 minus 0.126. That is sigma n. Now what is my stress here? This portion. Now as my bending is positive, if bending is positive, that means bend downward. This will be in tension. This will be in compression. So tension here. Why? If bending is positive, that means beam will bend downward. Tension bottom, compression top. So here my stress will be sigma mc over I rule. C1, C2 whatever you call, make sure it is this C. This value, this C. You can name it C1, but that doesn't matter. So 209 keep it. What is our C? 16.4. What is our I? 12,899 inch cube. So inch to the power 4. Inch here, inch to the 4 here, keep feet. So we have to multiply by 12 here. Okay. Multiply by 12 to make it keep inch. So if I do the calculation, 209 times 12 times 16.4 divided by 12,889. If everything is good, I found 3.191 kSI. What is the value here? 209 times 12. What is this distance? 16.4. Total is 24. 24 minus 16.4. That means this distance is 7.6 inches. So this is 7.6 inches. So 7.6 inches divided by 12,899 is to the power 4. 209 times 12 times 7.6 divided by 12,899. I got here 1.479. 1.479. So this is keep inch is to the power 4 after the calculation. Again, that is something to remember. 7.6 here 16.6 because this distance is larger. 7.6 here. So that is something to remember for T section or any irregular section. If it is rectangle, if it is this is rectangular section, 50% here, 50% there, very easy. This time not so easy. So what is my stress? 1. So negative 1.1.479 constant here KSI. Okay, I will erase it to clean. My stress here 3.191 and 1.7479. Here 1.479. So all the values are KSI. Right here somewhere KSI, 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 KSI. Then if I combine, what is the maximum stress? So here negative, negative. So 1.479 plus 12.126. I got here 1.605. Here I am getting 3.191. It is plus, it is minus. So you have to minus it. Minus 126. 126. Here I got 3.065, and that is plus, that is minus. So if I draw the diagram, it is increasing, it is decreasing. So my value here will be, now will be this. So is no longer 0 at the neutral axis, because this value is increasing, this value is decreasing. My curve is moving, shifting. Okay, so this is my final maximum axial stress in tension zone. Maximum axial stress in compression. So this is maximum axial in compression. Actually, both are answered. So our answer is maximum shear stress, maximum axial stress. So this is maximum axial stress in tension, maximum axial stress in compression. Ideally, we are concerned about this, not this one, because if the beam can take this amount of stress, it can obviously take this amount of stress too. Okay, so what is the final answer? Maximum axial stress 3.065 KSI, maximum shear stress 0.395 KSI. So hopefully you understood how to find maximum shear stress, maximum axial stress in non-symmetric beam section. Now, if I revise, we do not need to draw diagram every time. If we know where is the maximum moment, maximum shear, we can find directly. Sometimes your problem might give you maximum shear force, maximum moment handy. Then you do not need to do it. And then centroid, if you do not know centroid, you have to find it. If you do not know the moment of inertia, you will have to find it because you need this. Okay, so today we will wrap up here. Thank you for watching.